Hey, here we are back again. I hope you've had a look at Polynomials Part 1, where we looked at the meaning of a polynomial expression, because now we want to investigate them further. And what's the sort of things we might want to do? Well, have a look around the screen here. Obviously, graphing the function here, this graph, is something that's going to interest us a lot. And just to track out what the important features of these functions are. And I put the function up here in a couple of different forms. There's your polynomial, many terms, and there are 4 terms there. And then I've written it as a product of factors. Okay, and that's what we're about here. Roots, zeros, and factors. What do they mean? And what do each of those ideas contribute to our understanding of polynomials? And then I've made an equation where I've put the factored form of the polynomial equal to 0. So each of these forms are going to be used here to help us understand the difference between roots, zeros, and factors. So let's have a look now at this particular function. I think you can see, first of all, that it's a cubic over here. So the graph looks like this. And then if we factorize it, can you use those factors? So these are the factors here, the 3 terms which multiply together produce the function. And what are we doing over here? We're putting that factored form equal to 0. What would that mean graphically? Well, where is a function 0? So y equals 0 here. Hey, I've seen that before, have you? They are the x-intercepts. So what we're going to do now is say if we can factorize the function, we can solve the equation equals 0. And where a function equals 0 is called the x-intercepts, or sometimes called the zeros of the function, where the function takes a value 0 all along the x-axis. And here they are here, neg 1, 1, and 2. And of course, I guess you remember, I hope you do, why we can easily find those zeros, or the roots of these equations. Hey, what's that? I've just stuck one in there. The roots of an equation, or the solutions of an equation. And this equation, of course, putting the function equal to 0, also produces what we call the zeros. So the roots of that equation are the zeros of the function. Important, we'll come back and look at that. But how would we get it? The null factor law, mate. You're right. A product of factors is 0 when one of the factors is null. That is 0, or this one's 0, or this one's 0. So we get the 3 values here. This one implies x is neg 1, check it on the graph. This implies x is 1, and this implies x is 2. So they are the 3 values. So that's what we want to distinguish, a little bit of terminology now. So come on down and let's check out this stuff a bit more. So here we have what we're talking about. A 0 of a polynomial is the value of the variable which makes a polynomial equal to 0. Very good. And that's what we're doing here. We're taking our y expression and putting it equal to 0. The roots of an equation are the values of the variable which satisfy the equation. So the roots of the equation could be the same as the zeros of the polynomial if the equation is putting the polynomial equal to 0. Okay, so are you getting confused? So the zeros here, the values of x to make this function 0, are neg 1, 1, and 2. Which, because it's being put equal to 0, these are also the roots of this particular equation. So just remember now, an equation has roots, a polynomial function has zeros when you put it actually equal to 0. Just a little technicality there. A 0 is the value of the variable which makes a polynomial function equal to 0. All right, so here now, just to confuse you a little bit, the roots of the polynomial being 0 are the zeros of the polynomial. So when you use the roots of an equation, that equation has to be the polynomial equal to naught for the roots to be synonymous with zeros. That's what they're trying to get at there. The roots can be of any equation if they are the equation where you're equating the polynomial to zero. They become synonymous with the zeros of the polynomial. Do you get it? I'm going to test you a bit later on down here. So come along and let's have a look. And here's your test. Okay, so this the screen clippings here are from Hayes and Harris publications. So you might get hold of that book and have a look. So if I stick x is 2 into this polynomial function, so we could call this p of x polynomial function, then when you stick x is 2 in there, you find that value of the variable gives you the answer 0. So therefore 2 is a 0 of that function, and 2 is also therefore a root or a solution to the equation where we put the polynomial equal to naught. So the idea is here, of course, that a number is a root of an equation, and a 0, a number can be the 0 of a polynomial function, meaning it's the value of the variable, which when you sub in gives 0 for the function. Okay, of course the answers here are the same as each other because the equation is where you're putting the function equal to naught. Okay, so down here I've got some screen clippings of the Casio 9860 Plus graphics display calculator. Great calculator it is, and we're in graph mode. And I've graphed that function there. And then what have I hit? Well, I hit Shift and then F5. You might see in there G-solve. It means solve the graph. In other words, have a look at the graph and try to pick out characteristics. There's a few characteristics along here which you can find using this software on the Casio. Can you just look at this line here, have a look along this line and see if you'd like to make a comment about any of the entries there. Have a look and maybe pause the presentation, just think about it. All right, so having a look at it, which one would you perhaps make a query or comment about? Well, we've been talking about roots, so here it is here. So we're looking at a graph. What's the wording now? We're looking at a graph, and the calculator is offering us a solution, a G-solve value for the root. Hey, hang on, is that completely correct? What do you think? No, because the root up here or for anything, or can only be for, not anything, can only be for an equation, can't it? You can't have the root for a graph. Okay, so what they really mean there is the root of the equation where the polynomial is put equal to naught. So they're a bit naughty here. What word should they have? Ah, you're right. 0. The 0 of the graph or the function where it equals naught. The root is really restricted to any polynomial equation solution of that. So that really would be nice if that was 0 in there. Anyway, are you getting your head around this terminology? Let's go down, we're going to do some stuff now. So here's some problems for you. We'll just go through this example here from Hayes and Harris publications. Here we have a quadratic and a cubic, and we want to find the zeros of that function. So that is, when is the function equal to naught? And so we're going to use the formula for the roots of a quadratic using the discriminant, b squared take 4ac, the Greek capital delta for discriminant. And when we stick our numbers in, neg b is plus 4b squared 16, take 4 by a by c, we are getting complex conjugates here. And if you cancel, remember cancelling into a sum in the top line, it's got to be cancelled into both of those terms. So it's 2 plus or minus 7i are the zeros. And you might extend that and say, therefore, what are the factors? Okay, so that's a 0. x minus that value and x minus the other value would be the factors. Okay, remember the connection there between zeros and factors, because if we wrote those as the factors and put equal to naught, we'd be putting this one equal to naught and this one equal to naught, and we would rise to those zeros. So I want you to be able to flick between the zeros, the roots of an equation, and the construction of factors. Let's remember here, this is the null factor law in operation here. All right. Okay, so what about this one over here? Okay, so we want to put it, we want the zero, so we're putting the function equal to naught. We can factor out the z, and then can we factorise z squared plus 3? Well, I hope you saw the presentation much earlier on complex numbers. Otherwise, you have to go back and have a look at that. And so it's z plus I root 3 and z take I root 3. So the zeros are those three. So this is a factored form here. Okay, what about this? Z squared plus 3 equals naught implies z squared equals neg 3, which means z equals plus or minus root 3 times root of neg 1, which is I. I'm just recapping that, because this line here by the null factor law, either that's 0 or this is 0, and that's how we get these two factors, if you like. All right. Coming to bring some stuff together, one of the interesting Huddyisms is that maths is sequential. The learning of mathematics is sequential and cumulative. Okay, so you've got to remember stuff on complex numbers. Even though we're working with real polynomials, remember factors like this or zeros like this can hide. There's no indication in the coefficients of that cubic that we've got complex solutions, but they can hide in there, because we learnt that back in complex numbers. Okay, the sum and the product of a conjugate pair are both real, and so they hide in there. Please keep your learning going here. You're learning stuff in sequence so you can build up a knowledge base, and you must accumulate it. Don't forget it. All right, so what I want you to do now is to find the zeros for these, what is about 12 functions here, using the same sort of process. Okay, so pause the presentation, check these out, and then come and check your solutions. Just check them as you go, forward it on and toggle on and toggle back, so you don't perpetuate a mistake. All right, let's have a look at solutions now. Okay, there's question 1 up to F. Just watch the factorisation there, how we get the zeros. And then question 2. Okay, now this is an important skill for later on, so it's worthwhile going back and just making sure you've got your head around that stuff. All right, moving on now, let's have a look at another example here. So again, we're finding the linear factors of a couple of functions here. So first of all, you might find the zeros. So put the function equal to naught, use the quadratic, get that, and now we're constructing the factors. Imagining that if this was the solution and this was the other one, the factors would be under the null factor law, z take and z take, so that you would solve that equation for getting the zeros. So the factors are these two, z take, let's say z take alpha and z take beta. Here, if you like to think of what you're doing here, with the idea that if they were zeros, that makes that 0, and by the null factor law, either this one is 0 or this one is 0, giving you the alpha and the beta. So what we're doing here is actually going backwards up to there. Okay, what about this one over here now? Okay, so here we are. We've got a common factor of z, and then we've got a quadratic. So we will solve this using the formula z neg b plus or minus the square root of the discriminant over 2a. When we do that, what do we get? We get a half and neg 3. Or you might like to just factorise it by reversing FOIL. Factors of 3, neg 1 and 3. Factors of 2z squared, 2z and z, and just fiddle them around. Okay, so you've got to remember your stuff from before. Remember, sequential and cumulative learning in maths. All right, you want to try some? Come down here and let's have a look. What are the linear factors of these? So find the zeros, take out any common factor first, find the zeros, and then constructing this sort of idea, which under the null factor law, then these will be the zeros. So study that one. So I want you to pause the presentation and have a go. I'm going to show you the answers now. So come down here. Okay, so there's question 3. A few parts there, 6 parts there. Let's look at question 4. Question 4, a bit more theoretical one. So study that one carefully and just make sure. I might ask your teacher to go through this and just check out that you fully understand what's going on. All right, let's develop a bit more. I hope you're getting confident with handling these expressions now, because we've come across these polynomial creatures and we want to get up close and personal with it. Let's remember, just don't learn the method, but try to see what's actually going on. We want to get that level of, I see it, I'm up close and personal with maths, because maths is fun then. Okay, so we're going to go backwards now. If we've got zeros of these two, can we reconstruct the function? So first of all, let's pick on this pair. That's a conjugate pair. Neg 3 plus 2i and neg 3 take 2i. And if we add it up, we get neg 6. And if we multiply the two together, difference of 2 squares, we get 16. Let's just check that. This will be neg 3 squared, which is 9, take the second one squared, because this is of the form a plus b by a take b. Old stuff, a squared take b squared. So it's neg 3 squared, which is 9, take 2i squared, which is 9, take I squared, times 2i squared is 4i squared, which is neg 4. I squared is neg 1. So that's how it comes to 13. Negative by negative is a positive. And this was old stuff, because we know that if we have a conjugate pair of for the solutions to an equation, then what we have is they hide, there's the minus the sum of the roots and the product of the roots. They form a real quadratic factor. There's no i's obvious there. So we've made a quadratic factor out of that by saying, let's look at the sum and the product of the roots there. Okay, and then a half, well, we could, if you could say z take a half, that's the most sort of natural response to what's the other factor that gave rise to this half up here. But of course, neater than that would be to say 2z take 1 is a little bit neater. Okay, so we could say that. Okay, so either of those would do. But just watch now. Look at this italics up here. Look up here. In italics, that should draw your attention to it. All the cubic polynomials. So it won't do just putting through there the quadratic factor times one of those linear possibilities, z take a half or 2z take 1. Because you could have a whole family, any scalar, any ordinary number, multiply that by that polynomial, would have the same zeros, wouldn't it? Because if we put this equal to naught, then either this would be naught or this would be naught, giving us the zeros that we started with. This would not have any impact on the zeros, because it is a constant, and it's not going to be a zero constant, because the whole thing becomes zero that way. Okay, so don't forget the all. We're only constructing a basic parent function here, a parent function, and we could have any scalar multiple of that. Okay, so, and we just want the function who's zero, so we wouldn't have put 0 there, so our answer would be p of z equals that. Okay, your turn. So come and have a look. Here are pairs, well, a couple of pairs, and well, there's 3 in each of these here, but we've got, looks like conjugate pairs everywhere. And what's the answer to that? Why have you got conjugate pairs? I think it's got something to do with the fact that we're doing real polynomials here. And so they must, all the complex roots must occur in conjugate pairs so that we can have them hide in quadratic factors and not be obvious from the coefficients of those quadratic factors. Because we're talking about real polynomials that only have real coefficients. Remember all this stuff. Okay, have a go, and I'll show you the answers now. Okay, so there's question 5. And we've got them paired up, make the quadratic factor, and then multiply by that linear factor. We're talking about real polynomials here. Real polynomials, and that means the coefficients are real. We can't have i's in there, which implies complex roots will occur as a conjugate pair. Okay, so they can hide in the quadratic factor. Okay, so keep thinking about that. Okay, come on down, let's do a bit more. And here's another little twist-a-rooney to the same idea. You can see what we're doing. Roots, zeros, and factors are all intimately entwined. Here we are, watch this italics here. All quartic, degree 4. They've got zeros of 2, -3rd, and that. So what are you going to do? Let's start with the conjugate pair. Find their sum, find their product. So these are the coefficients we want. So the standard form for a quadratic, a simplest quadratic equation or function with those zeros would be z squared minus the sum of the roots by z plus the product. That's the structure, isn't it? So here we are, minus that sum is plus 2z, and plus the product is -4 down the end here. That's our quadratic factor. Now what about the linear factors? Z take 2 is easy, and the other one could be z take -3rd if you wanted to. And that is z plus 1/3, but it's probably better to put it neatly as 3z plus 1. Just note that this does give you, this factor would give you a 0 of -3rd. Just check that. So this is the preferred here. If we put that, it would not done apply. If we wanted that to be 0, to give that 0 there, then that's what we would do. All right, so let's put it all together now. The two linear factors, the quadratic factor, and don't forget your a, because this is the scalar where it's not equal to 0, so I should put that as well, representing the whole family. Okay, how are you going? Getting a bit repetitive, so build it up, do some practice. Let's come down and have a look at some practice here. Here we are, find all quartic, but don't forget to put your a in front, and at the end that a is not equal to 0. Pause the presentation, have a go, and I'm going to show you the solutions now. Okay, so there's question 6. Are you getting the hang of it? It's getting a bit repetitive. Think about it. The underlying idea, of course, is we're talking about real polynomials, and therefore creating factors. Those factors must all be real. Well, if you broke it out linear factors, you might have something like z take 2 plus root 5i, 2, well, we'll just use this bottom one here, 2 plus 3i, and 2 take 3i. So you could have some, complex linear factors here, but they will combine together to give the real quadratic factor there. So at the end of the day, they've got to hide. But you could have a product here of linear factors where you can see the I before you multiply it out and make the quadratic with real coefficients. Are you getting the idea? Let's keep going. It gets better as you get more familiar here. Okay, what we're going to do now is, having broken down individual polynomials and looked at graphs and solutions to equations, roots to equations, we're now going to look at what makes two polynomials equal. They must have the same degree or order. And this is the highest power occurring, is the order or the degree of the polynomial. So obviously a 2, which if two polynomials are aiming to be, we're trying to find if they're equal, you must actually have the same set of powers. The highest power must be the same, and all the corresponding terms must have equal coefficients. So each term has to match up with an equal term from the other polynomial. Okay, let's have a look at what we're going to do with this. Here we are. So can you construct a polynomial equal to this one where we know that one of the zeros is a half, so one of the factors is 2x take 1, and we don't know the other factors. So we could say we're making a cubic, so the quadratic that's missing would be ax squared plus bx plus c. Can we make up this, an equal polynomial to this, in factored form? So this is sort of a reverse way of finding factors. So we're going to develop that in a minute. So if these two are equal, then expanding this side, doing all this work here, and then that by that, we did this earlier, this idea in part 1, doing the basic expansions of factors and to produce a polynomial. And so we've got that. Now we've got to collect up the terms. So we see some here, 2bx squared, neg ax squared. So the overall x squared term from the right-hand side expanded is that, 2b take a lots of that. Now let's have a look at the x's here, 2cx take bx, so we've got 2c take b lots of x take c. Now if these two are going to be equal, then we can equate coefficients. Okay, so the 2a, the coefficient of x cubed, must equal 6. And then the x squareds is 2b take a over here has to equal 7, because that's the x squared term there, and so on. So the neg 19 is going to be the same as the 2c take b over here. Okay, and then the constant down the end must be the same, so 7 equals neg c. So we can say the easy ones, 3 and neg 7, and then we're going to solve these two equations simultaneously, or, well, you don't have to actually do that, you can solve it here. 2b equals 10, b equals 5, check it over here, b equals 5 implies neg 14 take 5 equals neg 19, which checks. You should make sure that, and they've said here b equals 5 in both equations, I would rather you spelled it out, solved one and took it across and shown that that is a solution, a common solution with the other. You can't just not check it. So it must be a common solution for all equations containing that particular unknown. So we've found it. And more importantly, we now have our original polynomial in this form. 3x squared plus 5x takes 7. And we could go on and find where that function cuts the x-axis by finding its zeros, wouldn't we? We'd have one here, and then we're solving this, we'd find the other. And would there be 3 zeros or not? It depends really on whether this gave us complex conjugates. Can't plot those as intercepts on the real axis. So maybe it's only got one real zero here, one intercept on the x-axis, and the other might be complex zeros in a conjugate pair there. How would you tell? Maybe check the b squared take 4ac, mate. We're going to be doing that in a minute, a bit later on here. And I think you'll find it's got 3 real zeros there. So b squared take 4ac, I think, is greater than 0, isn't it? Okay, so we'll come back to that. Just depends on whether you want to think about this a little bit ahead of the game or not. Okay, so here's exercise 3D. Got a few here where we've got equivalent expressions with undetermined coefficients, we say here, when we don't know the coefficients. So I want you to use that process that we've just done, expanding and then equating coefficients and so on. All right, pause the presentation and have a go. I'll show you the answers now. Okay, look at the working there and just make sure it's nice and clear. and that you come up with a solution which flows well, and you can see exactly what's going on. Right, okay, so what we're going to do now, you might have just a look at this. I've used detached coefficients to do a shorthand multiplication of the two polynomials over there. I think we just generally do it by an extended FOIL, every term in the first bracket by every term in the second. But you can do this if you wish. I think it's not very beneficial for just a multiplication. All right, okay, come down and let's develop it, and we're nearly finished here now. What we're going to say is if we had a quartet, could we construct two quadratic factors? Okay, z to the fourth plus 9. Notice there's another way of doing this, isn't there? Z to the fourth plus 9. You could actually write that or try to write that as factors using the zeros, z to the fourth plus 9 equals 0, which is z to the fourth equals neg 9, and try to do something there. You could do something there. But another way of doing it is to say, well, let's construct a pair of quadratics with undetermined coefficients. Now, how many need to be undetermined? Well, z squared by z squared will give z to the fourth, and factors of 9 are 3 and 3. So we're going to cheat a bit and put those in and say, is it possible to create two quadratic factors with the same constant on the end and just differing z terms? And the answer is, of course, let's expand this side. Okay, let's expand the right-hand side, and here it all is here. So it's all the terms that by that, etc. 9 terms there, and there they are, the first 3, 6, 9 terms. And of course, we've constructed it so that one and that one already match. But a plus b, lots of z cubed, must be naught. The original function didn't have any of them. And a plus b plus 6, lots of z squared, must be 0 as well. The original expression over here didn't have any z squares. And 3a plus 3b must be equal to naught because it didn't have any z's either. Okay, so equating z cubes, z squareds, and z terms. So then let's go down here. B is equal to neg a. That's from 1 and 3, these two. So you can then sub that into ab plus 6, getting here a quadratic only in a, so a squared is 6. So a is plus or minus root 6. And so when a is positive root 6, remember we said b is neg a, b is neg root 6. Just notice the upside down of these two. That's indicating that b is the negative of a. So if a is positive, it mates with a b which is negative. So there are our two solutions. You could have root 6 for a and neg root 6 for b, or neg root 6 for a and root 6 for b. It gives you the same answer, doesn't it? The final factorised polynomial would be this root 6 z plus 3 z squared take root 6 z plus 3. So the idea is that this is the opposite sign of that one. All right, some interesting stuff. Ways of dissecting polynomials and getting up close and personal with different ways of representing them. Okay, we'll come down and I want you to have a go at these three questions here. Right, so pause the presentation and just see what you think. And this is an interesting one. So play with that a bit, because we are looking at a possible alternative to factorising in the conventional way, of actually constructing two factors and seeing if we can determine what the coefficients might be, here's one here, for that factorised form to work, to be equal to the original polynomial. Right, pause it, have a go. I'm going to show you the answers now. Okay, so there's 2a and b. And again, they've used this long multiplication, detached coefficients to shorten the multiplication. we can just do this if you wish. Okay, let's look at question 3. There is question 3. Okay, and question 4. Okay, so study those solutions carefully, particularly the discussion of why it doesn't work. And again, talk it over with your classmates and teacher. It's good to use a dialogue approach to learning maths. It's good to talk it over and hear people explain it and talk about it in different ways. All right, finishing off, let's come down now and have a look at this one. We've given a factor of some polynomial. Here's the polynomial, and we know that x plus 3 is a factor. So find a and the other factors. So we can say x plus 3 is a factor, so the other factor must be what? Well, see the x cubed? We need an x squared term, so we know that must be that. Now it's a 3 on the end, and it's got to give us 6, so we know that. So the only place we need to put an undetermined coefficient is in front of the x there, bx. So don't put too many a's and b's in. Don't put a letter here when you know that if that's a 3 and you want a 6, that's got to be a 2. So use your knowledge a bit about expansions rather than just slap in undetermined coefficients through the whole expression. Okay, so just rub that out because I want to now show you this expansion. So we're going to go that by that, that by that, that by that, and get our first 3 terms, and then the same thing here, the other 3 terms. Collecting up the x squareds, there's 1, there's 1, so you've got b plus 3, lots of x squared. Here's a 2x and a 3bx, so it's 3b plus 2 lots of x. And now, therefore, we can start to equate. Well, the x squared term over here is a, and the x squared term over here is b plus 3. So a equals b plus 3. And then the x term over here is -7, and over here is 3b plus 2. So 3b plus 2 must equal -7. All right, so if you take this one first of all and solve it for b, and then substitute it over here, then a is 0. So what is our factorisation then? Just checking it, what's our actual factorisation? So if we solve this one over here now, then you'll have b is -3. And if we substitute that in here, with a is 0. So going back to our original, it's x plus 3, and then x squared plus bx, which would be -3x plus 2. And we've done it. In fact, we could then use the opposite to FOIL to factorise that, and we've actually factorised that cubic, knowing just the starting linear factor. So a pretty powerful tool for getting into factorisations of a polynomial. All it needed up the top here was that you knew one particular factor. Okay, have a go. Here we go, down here. There's your question. Oh, go too far down. We'll just come up here a little bit so you can't see the answer. Okay, so we've got one factor in each case. Make up a quadratic equation with the minimum number of pronumerals there. Okay, in the factorised form. A quadratic with a minimum number of undetermined coefficients. Okay, because some things you know. That one and the end term you'll know. All right, have a go and pause the presentation. I'm going to show you the answers now. Well, here we go, question 5a and b. And let's move on. Last one, I think, here. Last little example of using this stuff. So this time we've got a quartic, same idea, and we've got 2 factors given to us. So we can say they're the 2 factors, and expanding that to a quadratic, making up an undetermined quadratic here. Now, it's 2x to the 4th, so we've got 2x squared here, we know that that's going to be just x squared. So when they're multiplied, it's 2x to the fourth. Let's look at the other term we know, the 3 down the end. So when we create this quadratic, it's neg 3. So to get 3 on the end, it must be neg 1, because those two are the two terms that will expand to give a positive constant at the end. So now, expanding this whole quadratic here, product of two quadratics, sorry, expanding it, they've shortened this, they haven't shown the terms as such. Do you need to expand the whole thing? Well, what they have said is to get here, you could just look at how do you get an x squared term. It would be, first of all, the x cubed term would be that by that, and then that by that. You could do that. I think you should just expand completely and then collect the terms up. It's a bit safer than just plucking them out. Okay, and so they've left the steps out here of equating those. So you might have a look at that and just check that you get these coefficients, or the equality of these coefficients. Okay, and then you can solve them just going down there. Okay, so you need to expand this fully, I think, and collect up the terms as we did, then equate coefficients. All right, so down here then, once you have done all that, of course, you've got the factorised polynomial. We were given these two. We can now work out that undetermined quadratic factor, and then we can do the zeros and find the zeros coming from this one, which is going to be formula for the roots of a quadratic again, this one here. So the zeros are that, and they would be the points where the function is 0, the x values make the function 0, which of course is where it would cut the x-axis if you're looking at it graphically. All right, here you are. Finish up with having a go at these now. Oops, let's just go up a little bit. Some quartics given two linear factors. Are you seeing how to look at polynomials and how to break them down? Hope so. All right, pause the presentation and have a go now. And here's some answers, 6A and B. See what you think, check it out. And we do have one more here. Okay, so that's where we are given a cubic with a constant down the end, which is unknown. But we're told there are two identical linear factors, and hence write the polynomial as a product of linear factors. Okay, so let's concoct a statement here. See, if there's two linear factors, that would mean x take a repeated, or x take a squared. And let the other one be, now don't put in too many pronumerals here. So we know it's 2x cubed, so when we square this term, you'll get x squared, so this is 2x, you give 2x cubed, and then we do need the b here. See, what they've got here is you don't need an a in there or another letter in there, because you know that coming out of here will be x squared times 2x will give 2x cubed. Keep the number of pronumerals to a minimum. Okay, so expanding that perfect square, timesing by that, they've done it with their shorthand thing. I would just expand them all again, this by this, etc. And so we can collect up the terms, x squared term, x term, and the constant, and then equate them. So there's 2 in front, b take 4a is the x squared term, so that's the 11 from there. The x term is 2a squared, take 2ab, which is there. And so we get our three equations. So now we've got to solve these. So that's a bit of a problem, but what we can do is take an expression for b from number 1 and sub it into 2. Okay, b equals 4, neg 11 plus 4a, and put it into 2. We get a quadratic then in a. So you get two values. It's a bit complicated now. And then we can look at what those values are. So if a is 2/3, 4a take 11, which is b, is neg 25 over 3, and then subbing it into the k expression down here, we get that solution, and then when a is 3, we get that b, and subbing it into the k, we get that. So there's a few possibilities here. So the possibilities are k is neg 100 over 27. The function looks like this. If k is 9, then the function looks like this. So a couple of different ways of factorising that, if you like. Okay, so that's the most complicated one, where you've got a fair bit of unknown stuff there. Okay, have a go at some down here. All right, so here we are. It's two identical linear factors. So the same idea here, and prove that. So you need all the details that c is either 5 or neg 27. All right, similar here, similar approach. So have a go. I'll show you the answers now, and then we're finishing up. Okay, so there's 7a, and 7b is there. So, how are you going? Feeling a bit more confident about how polynomials are made up, what their graphs might start to look like, how to factorise them, and so on? Hope so. Anyway, what we're going to do is finish up now, and I'll catch you in the next presentation. Cheers for now.